Tí sábẹ́nu láti máa ẹni tẹ́bi máa ń fi ọkọ̀ Gaba lẹ́tà sáré ọ̀gbẹ́sọ̀gbọ̀n tẹ́ńtẹ́ àti ìwé náà ìfẹ́sà.
Good morning, everybody. I've muted all of you because some of you just like complicating matter. Again, any question you are permitted to ask in the chat. Okay. I have sent the link and I've sent the online link as the YouTube link as well. So that's okay. So we need to move faster today. Okay. So we're here. Okay, so this was where we stopped last week. We started talking about first law, thermodynamics, thermochemistry. So we are still on our topic, but we have limited time, so I'm going to move a little bit faster. Some of the concepts you are familiar with. In case you have seen something on your slide on my slide that is not on your side, just please write it down. It's even a good habit for you to take notes. Okay, so we stopped at the concept of its Q, and that is energy transferred as a result of difference in temperatures. You can define temperature as the thermal energy that a system has. So let's move on. So there's a worked example here. Calculate the work associated with expansion of a gas moving from initial volume of 46 to final volume of 64 at a pressure of 15 atmospheres. So we have defined work as P minus P delta V, and our delta V is equal to this V final minus V initial. And we have defined work as negative because we are defining work from the point of view of the system, where the system is the part of the universe that we are interested in, the part of the universe that is of interest. So this gives, if you put in all the values, slot in all the values, as some, I know somebody asked that question last week, and I'm going to repeat it again. When you're given anything, just for the purpose of uniformity, it is always a good idea to work in SI units, unless otherwise stated. It makes your work more transferable between colleagues or whoever you are working with. Okay, so slot in our values. W is minus 15 times, this is the pressure that we wrote here in pascals. That's the SI unit for pressure. Volume is 64 minus 46. So to convert it to SI unit, we multiply it by 10 to minus 3. And we have the value for our energy in joules. 2 seconds for you to look at the example enough, and moving on. For those of you online, I'm also trying to read your comments anyway. So on YouTube, so you can also send questions there as well. Another example there is calculate the heat absorbed. Let's work this example later because I've not described the concept of specific heat capacity. It's coming ahead. Okay. So internal energy, so that's supposed to come out more. So we've defined W, that's work as a result of force moving through a distance, and heat as a result of difference in temperature. So I said that we'll work the second example, we'll work it later. So internal energy, we defined energy as a capacity to do work or transfer it. Now, there is the concept of internal energy. That's the energy that the system in itself possesses. So the internal energy of a system is the total kinetic energy or potential energy as a result of the spatial arrangement of the constituent atoms on molecules. So you can put it in a different way, as a result of the atoms that are present or molecules that are present in a molecule. Each one has its own inherent energy. And because of the way they are arranged, there's also another potential energy with it. I've sent the YouTube link, please. Let me also share it here in case you want to share it with your friends. I can see people are already there. So it's the sum of kinetic energy. The kinetic energy is due to the motions of the system's particles. So you have atoms that are in constant motion. They are moving around. We have defined, so one of the characteristics of gas molecules is that it continues to move around all over the place. It's allowed to move. So there are translational motion, straight line motion, rotational motion, that's a motion about an axis within the molecule. Then vibrational motion, those are oscillatory motion. All this motion, they all increase with temperature. So internal energy also increases with temperature. Then, but as a result of spatial arrangement, so you see the total kinetic and potential energy. So the potential energy is due to interactions between the particles within the system. So we're talking about atoms and molecules. Again, remember, potential energy is energy with respect to position, relative position of one substance with respect to another. And at the beginning, there was something that we said about electrostatic potential energy. So you have charges within the molecule that leads to different energies. So one of the potential energies that you have within the molecule, you have the static electrical energy, you have nuclear energy, and then you have the energy stored in the chemical bonds. So we're saying a lot of energy because energy is the core concept that we deal with in thermodynamics and thermochemistry. So the internal energy accounts for all this microscopic energy that we're talking about, all those little tiny bits of energies that are present in the molecule. So one of the characteristics or some of the characteristics of internal energy that number one, it's very difficult to measure the absolute value of the internal energy because you have to put into consideration everything down to the smallest atom present in the molecule. Imagine you want to calculate the internal energy of a human being. You know all the carbohydrates present, all the proteins present, you have to calculate them in detail. So maybe human being is complicated. Even if you want to calculate the internal energy in 1 mole of a substance, Avogadro's law tells us that 1 mole contains about 6 times 10 to power 23 particles. So you have to take, so that's just 1 mole. So if you're talking about 10 to power 23 particles, substances, you have to account for each one of them. So the absolute value of the internal energy is always difficult to measure. However, the change, so you're going from, your system that we are studying is undergoing changes. If it's undergoing changes, so that means you're going from one state, we label that state A, or state 1, or initial state is going to another state B. So when you are saying about these changes, it doesn't mean that you're taking, for example, your test tube from one place to another. No, it might just be a simple change of state, as in you are adding heat, you are heating the system. That's a change of state. Once you heat the system, you have done work. If you have gas and you compress it, you have changed the state of the system. So anything can change the state of system. So the internal with each change in state of the system, the internal energy changes, and we represent it as delta U. Sorry, U is the symbol for the internal energy that we're using in this course. Depending on the textbook that you take, even the one that I recommended, I think the symbol used for internal energy is E. Or the symbols might be different, but the concepts are the same. So please note that. So we're using the symbol U for internal energy in this class or in this course. So when you have this change in internal energy is easier to obtain, and it is more meaningful. So where is it? So U, difficult to measure, delta U, easier to measure, and also more meaningful. So let's move on. So the beautiful thing about the delta U being the meaningful part is that internal energy is a state function. When you say something is a state function, it depends on the state. I'm not sure the YouTube video is not clear. From what I'm looking at, it is clear from here. Please check your internet if your YouTube video is not clear. Thank you very much. It is actually very clear. So please check your network. Okay. So internal energy is a state function. What is a state function? So when you say the internal energy is a state function, it simply means that it depends on the state you are in. Our state, the state of a system, the state of a system is characterized by temperature, volume, pressure, number of particles, the entropy, and so on and so forth. All these things, we call them state variables, thermodynamic or state variables. Once you change temperature, the state changes. Once the volume changes, the state changes. Once pressure changes, the state changes. Once the number of moles changes, the state changes, or the state of the system changes. So, what am I trying to say in essence is that, so the internal energy depends on these things. It does not depend on how you arrive at it. Let me give an example. For example, there's 50 grams of water at 25 degrees centigrade. You only need to know that what you have is 50 grams of water at 25 degrees centigrade. It doesn't matter whether that 50 grams of water that you got to, you obtained it by bringing out ice from the freezer, or you obtained it by cooling down water that you got from cooling down water that you get from temperature on the boiled water initially. All you need to know is that it's 50 grams of water at 25 degrees centigrade. So that's what we mean by state function. It depends on the state. And the other part of it, that's one thing. So anytime that you say you change the state, the beautiful part is that once you change the state of the system, because it's a state function, the change in internal energy, it's just the final, not so final minus initial. Let me please correct that. So it is U state B minus U state A. So you're going from state A to B. You're going from an initial state to a final state. So it's U final minus initial. It depends only on the initial and final states. So if we're looking at a reaction, considering it's a reaction, so it is the internal energy of the product minus the internal energy of the reactant. So like we said, it is difficult to measure, but the change is not difficult. The change can be monitored by doing work or by supplying it. So you can measure that internal energy by knowing the amount of work that is done, and you need to know the type of work that is done too, because that matters. Why? Because it and work are not state functions. They depend on how the state was achieved. So the work done to melt ice, and warm it up to 25 degrees is different from the work done to cool water from 100 degrees to get to 25 degrees. So it and work, they are part dependent. So we can determine U experimentally by applying the first law in relationship to Q and W. Is there a question there? Please, again, refrain from unnecessary. I'm reading your comments because I'm looking out for questions. Please, useful comments like if it isn't clear, adjust the quality to that's fine. But abusive words, please refrain from that. It's not helpful to anybody. So the first law of thermodynamics in its simplest form, before we go to the mathematical form, says that matter cannot be created and energy but not destroyed, but it's not that's complete, but can be transformed. Energy can be transformed from one form to another. So let's complete it. Cannot be created nor destroyed, but transformed from one form to another. So you can convert a potential to a kinetic energy, you can convert chemical energy to, but you cannot just create energy just like that. So in all these cases, converting kinetic energy to gravitational potential, chemical to heat, put the chemical to the total amount of energy remains constant. Another example of change in U. If you are talking about worked example, I think there are worked examples coming ahead. If I understand your question very well. Akinola. Okay. So in another way to state this, the amount of the energy in the universe is constant. Remember, our universe is the totality of everything. So when we say totality of everything, that means it includes the system that we are studying, including the boundary that separates the system and the surrounding. So everything under is the universe. Energy can be changed, moved, controlled, stored, or dissipated. There's much more information going on nowadays than in those days. So we can see that you can store energy, you can convert, you can. Anyway, so the mathematical form of defining the first law, the total energy remains constant. The total energy of the universe remains constant, and that when you're changing the internal energy, you can change it by supplying it or by doing work. So for a closed system, and let us remember the concept of a closed system, energy flows between surrounding and system. So, which means if energy flows, energy can flow as heat, energy can flow as work. So for a closed system, the change in internal energy is whether Q flows in or out, or work is done by the system. So simply put, delta U equals Q plus W. Q is heat, W is work. Emphasis on the word for a closed system. The types of system that we have open, and then we have isolated, and then we have the closed system. The open system allows you to exchange internal energy. So this equation will not be correct for that of an open system. So it will involve that you have some internal energy going out or some internal energy coming into the system. And for an isolated system where both energy is not allowed to leave. So the isolated system, delta U is equal to 0 for an isolated system. Anyway, for most cases, people are interested in closed system. You want to work on the system that you are working on. So that's why if usually you would see people say that the internal energy, first law, Q is equal to Q plus W. So we were looking at some sign conventions last time, and I told you that a slide was dedicated to it. So again, there is no question like I don't understand. It is not a question. If you cannot hear me, there's something wrong with your system. Unless a lot of people cannot hear me. Q is heat. So sign convention that we adopt. So this is our first law. The system has its own internal energy, and you want to change the system from an initial state to a final state. What is delta U? According to first law, it is equal to Q plus W. Q heat, W work. So thermochemistry or thermodynamics, we adopt this. This is a convention in chemistry. If it flows into the system, if you transfer it into the system, then your Q is positive. If it goes out of the system, then Q is negative. Same thing with work. If you do transfer work, so if you work on the system, W is positive. If you work, if your work is done by the system, W is negative. So take time to look at the slide. So same thing. If you lose energy, when the system gets energy, delta U increases. When the system loses energy, delta U reduces. Okay, so let me look at the question. I thought closed system has no work done. No, closed system, please go back to your slides. Closed system allows you to exchange energy. Energy, work is a form of energy. So if you are doing work on the system, fine. The common closed system that you see every day are your cars. So you combust fuel inside the engine and it's converted to work and the car moves. That's the work, the car is doing work. So moving on, I'm about to move on from this slide. And what I know is that those on YouTube might be a little bit delayed. 5, no question. 4, all those people that were asking me is exceedingly large question last week. They will come at the end of the class to come and ask questions. Week 1 gone. All right. Calculate delta U, not U, for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. Please always understand the English in the question. So we can calculate delta U by Q plus W. What is Q? It says an endothermic process. Endothermic, that means you're supplying it. Whether there is nothing like endothermic system. It's the endothermic process, an exothermic process. Endothermic process, endothermic process, an endothermic process, you lose, endothermic and exothermic. Exothermic, you lose heat to surroundings. Endothermic, you absorb heat from the surroundings. Moshood, it's because of you that I'm going back. So let me move on. Okay. All right. Okay, so Oreo first is 17 kilos. Oh, okay, you have calculated it. So now let's look at the question. Q is they say is undergoing endothermic process. So under endothermic process means that the system absorbs heat. So if your system absorbs heat, your Q is positive. So endothermic heat flows into the system. Work is done on the system, so your work is also positive. That means our delta U is equal to 15.6 plus 1.4, and the system's internal energy has increased by 17.0 kilojoules. A reaction is a process now. Your process can be a physical process or a chemical process. Okay, so moving on, let's work on another example. A sample of an ideal gas in a cylinder of an engine is compressed from volume 400 mil. This is not compression. So V1 is 400 and V2 is okay, so this is compression 400 mil. This is to 60 mil. I was looking at 600 mil. Apologies. Against a constant pressure, so P is 8 atmosphere. At the same time, 140 joules of energy is transferred from the gas to the surroundings as heat. What is the total energy change, total change in internal energy? Yeah, so we always know delta U is Q plus W. So when do we now use negative value of work? I don't know how to answer you that one. So the system is the ideal gas on the cylinder. So since the system transfers heat, now at the same time, 140 joules is transferred from the gas, which is our system. So Q is equal to minus 140. Now, because the gas is compressed, work done is on the system, W will be positive. But to make you understand that we always define W as minus P delta V. So, which is equal to minus P times V2 minus V1. Our V2 is 60 mil, our V1 is 400 mil. So if you put that into that expression, minus this into 6 times 10 to minus 5 minus that. Please, okay, winner, pay attention to this example. So your work ends up being positive because this will be negative. We have defined work as negative. So what I'm trying to tell you in essence is W is defined as minus P delta V because we are defining it as work done by the system. So if in the essence, the work done by the system is as a result of something compressing it, which is the process that took place, it will end up to be positive. So this is our work done. So our W will now be, so let's see, 100. So Abdul Rashid, your answer is not correct. Okay, so let's move on. So if the system, if for example, to switch it around, Toluwalashe, switch this around, if your V2 is the one that is greater, it is going to end up negative. Okay, so moving on, no other question of confusion. There's a third one. Time is against us. So the question here is gases A and B react in a cylinder with a movable piston. You know that thing that that thing that you cover something and then you allow it to move, even though you make it adiabatic. Sorry, not adiabatic. You make it not and to not allow particles to get out. So during the reaction, the system loses 1,150 joules of it. The piston moves down to the surroundings to do 40 joules of work on the system. So this is similar to the previous example. So it loses work done to the surrounding, work done by the system, on the system, sorry. So we have, only what is the topic? How would I answer that question now? Okay, so this is similar to that last question. And I am moving on. The slides should have been shared. I shared the, yes, Akintola, you are correct. I shared the, so you should check why is Q minus 150, minus 1,150. Does anybody want to reply? Wow. Quickly, I'm moving on. So Q is minus 150 because the question says the system loses it to the surroundings. Remember our slide. 5. Thank you, Rachel. 4. 3, 2. So I'm going to let you figure that one out, Isaac. There's no general way. You have to look at the question. You have to look at the question before you conclude. It's an experiment. Yes, so if system loses, it's an exothermic reaction. So there's a question here. If the system loses the work done, please, Mutiu Sifao, recast your question. I don't understand your question. All right, so let's move on. Enthalpy. So we have talked about internal energy. Another concept useful in thermodynamics is enthalpy, because this one measures the total heat content of the system. So it involves both the internal energy and an additional pressure volume work in establishing the system. Excuse me. So internal energy is a measure of the total heat content of a thermodynamic system at constant pressure. Okay. Given by U plus PV. Similar to the internal energy. What's environmental standard? The department, sorry. Similar to internal energy, absolute enthalpy is difficult to measure. However, the change in enthalpy is also more useful than its absolute value. Similarly, it is a state function, which means it depends on the current state of the system and does not depend on how you achieved that system. So it has almost the same characteristics as that of internal energy, except that it is just slightly more than the internal energy. So delta H is defined as H final minus H initial. So if you separate this out, it becomes delta U, U final minus U initial plus P delta V. I don't have space there, that's why I'm not writing it all out. The change in internal enthalpy is also equal to the heat of a reaction at constant pressure. So if you are changing the heat of a system at constant pressure, so you can change the heat of a system at constant volume, but that's not equal to the change in internal energy. It is at constant pressure, and that's why we have this tiny subscript here beside the P. For a reaction, in chemistry, we talk a lot more about about enthalpy. In chemical engineering and in anything that deals with combustion of gas in a small place, petroleum engineering, they deal more with internal energy because you're looking at constant volume processes. So enthalpy of a reaction that's associated with that's enthalpy associated with a chemical reaction. So the final enthalpy in such a situation is the enthalpy of the product, and the initial is that of the reactant. So A plus B going to C plus D. So the delta H of that reaction will be enthalpy of C plus enthalpy of D minus enthalpy of A plus enthalpy of B. Similarly, it is positive for an endothermic reaction and negative for an exothermic reaction. So these diagrams that we have here are ways to visualize what we are talking about. It doesn't necessarily mean that that is what the electrons are doing, but these are ways to just represent what we are looking at, what we are talking about in a diagram. So you often represent exothermic reaction. So you say that it's reactants going to products plus heat added. Reactants plus heat going to products for endothermic reaction. This expression that I wrote here is often called thermochemical equation. So a thermochemical equation, that's the one that shows the associated enthalpy change in the equation. So for example, in the combustion of carbon sulfide, to give carbon dioxide and sulfur dioxide, it has been measured that the enthalpy change for that reaction, the heat release is 1072. So the negative here tells us that it's an exothermic reaction, which means this reaction produces heat. So we can write this reaction as this. So carbon dioxide, carbon 2 sulfide, carbon 4 sulfide plus carbon oxygen, that's the combustion, to give CO2 plus SO2. Since it's an exothermic reaction, it also produces heat. So that's why we are using plus 1072 in this section. Yes, please. There is a difference between internal energy and enthalpy. As a matter of fact, H is equal to U plus PV. So there's this tiny difference. It is small, but when you're doing really, really very sensitive work, that tiny difference makes a lot of sense. So, and that's why I mentioned it before, that when you're working at constant pressure, you're looking at enthalpy. When you're working at constant volume, you're looking at internal energy. Yes, PV is work. So this PV, it is not the work that the system is doing. It's like a work that the system has internally with itself to keep itself stable. That's the best way that I can explain it at the moment at Whenu. So I want to give another example of a thermochemical equation. So this thermochemical equation, this is liquid water going to gaseous water. The change in enthalpy is positive 40.66 joules. And that means that we need to supply heat to convert it to the product. In chemical reactions, we do not use the negative sign. So our positive sign comes here. So the heat is a reactant going to product. So these are examples of thermochemical equation. This is another example. A thermochemical equation shows the associated heat change. So if I want to write this by including the heat, so I'm going to write 2Al solid. Please, when you're going to the nitty gritty, class reps, I have sent you the link to download the slides. Please share with your class groups. This is the fourth person asking about the slide now. So plus Fe2O3. Now there's something that I want you to note here. I'm writing the state of matter because when you're doing when you're looking at serious work, serious thermodynamic work, the state of matter matters. That's interesting. State of matter matters. So aluminium liquid is different from aluminium solid. Well, even to our eyes, we know that ice is different from water. So it's important to state the nature of the matter, the phase of the matter. So plus Al2O3 solid. Oh, apologies for that. So that's not there. Plus 2Fe liquid. So if I'm going to put this into the equation, I will be plus 852 kilojoules per mole. Okay, so what's the time? Moving on. Let me quickly move. So characteristics of H. I think I've mentioned this before. Why am I going back? Characteristics of H. One, it is a state function, meaning that it depends only on the states. Okay, so characteristics of H, and that's also another characteristics of U. They are both extensive. So when we say that they are extensive, okay, so somebody asked, why are we adding it to the product? Because it's an exothermic reaction. If it's an endothermic reaction, the heat will be added to the reactant. So back to this slide, they are extensive, meaning that they depend on the amount and state of phase of a substance. For example, if you increase the number of moles, thank you. If you increase the number of moles, no, I need to explain on how work. I'm coming. So let me explain this extensive first. So extensive means that it depends on the amount of substance that is present. For example, if you have 1 mole of a substance, the internal energy is different from having 10 moles of that same substance. Then there's something also here. It depends on the phase of the substance. The liquid water is different from solid water. The internal energy are also different. I need an example on how work is done on a system because I don't understand that part. Work is done on a so the example that we gave, when you compress, you increase the energy of the system. That's an example. That's one of the examples that we gave the other time. So considering systems that do not, so an electrical work will probably be charging of the system. So that's doing work on the system. Somebody is raising up their hand. I'm not going to allow you to talk. Please type your question. I'm trying my best to read question as I'm going along. Is there a formula to get heat energy released or gained from the chemical equation? I'm not sure I understand that question. So because each reaction releases a certain amount of energy. And one of the things about the data science that is in rave right now is that there are so many data that have been generated. So there was a time that what most people were generating was to generate as much. It's one of the things that was being measured is the heat of reaction of several kinds of reactions in order to understand some other concepts. So you would see a table, you get let me give it an example. There's an example, or there's a thing called the chemical handbook where you would see detailed reactions that have been carried out and their heat of reaction has been measured. I hope that answers your question, Chukwuemeka. So heat and Q are not the same thing. There's H, there's Q. So it is energy, Q is energy transferred across a boundary. H is energy content, the heat content of the system. There's something that I want to write here. Let me come back to that question in a bit. So so state function, H and U are state function, they are extensive. The enthalpy change for a reaction is equal. So the consequence of being the consequence okay, if that's the meaning, that's another way to look at it. I can't pronounce your Zine code or whatever. So Chukwuemeka is on YouTube. I was asking that question to which you are providing the answer. So the implication of it being a state function, I want to quickly round this up. Because we still have a lot to cover. And another lecturer is going to come in soon. The enthalpy change of a reaction is equal in magnitude, but opposite in sign when you reverse the reaction. For example, this is the change in internal energy when you convert liquid water to gas, which is steam. If you want to take the gas back to liquid water, same amount, same temperature, the reverse process, which we call condensation, is equal in magnitude, but opposite in sign to the energy that you used for the reverse reaction. So that's the thing about state function. The state function, this way, that way, same amount of energy is used, but different sign. So we say that they are extensive. Extensive means that if carbon dioxide is carbon, this is carbon monoxide going to graphite and oxygen. The delta H for this reaction, so this is the reverse of delta H of formation, is 110. If you multiply it by 2, you will have to make it 220 kilojoules. So it's no longer per mole now, sorry. It is kilojoules. Here is just 1 mole that we are dealing with, so that's why we have it as per mole. Again, I don't understand, I don't get. So so that's, maybe we should work this example before we call it a day. Oh, so I'm not the only one teaching this course, and I need to finish my own in about 2.5 weeks. So that's why I said we need to move fast. That's what I mean by another lecturer will soon take over. How much it is released when 450 grams of methane gas is burned in a constant pressure system. So constant pressure, that means we are looking at delta H. I said I was coming back to a question. What's the difference between Q? Q is energy transferred. H is energy content of the reaction and of the system. How much is released? So we're given this expression CH force 2 plus to get, so this is the equation again. And delta H of the reaction is minus 80. So 1 mole of methane gives 80.9. So it is an exothermic reaction because it is negative. So the question is how much it is given up if we are using 4.5 grams. So the beautiful thing is you need to know, so we know what 1 mole gives us. So we need to know how many moles are in 4.545 grams. And we know that the relationship between, you have a formula, you can calculate the molar mass. The relationship between the number of moles and molar mass is number of moles equals mass over molar mass. Okay, so Abiodun will see now if it's the same thing. So molar mass, we calculate the molar mass. That's the number of moles. So it's given off will be minus 250. I think there's another example that you can go through on your own because there's a possibility that you have another class now. Sorry, before I leave that, any question on that example? 5, 4, 3. Yes, of course, we're using stoichiometry. Stoichiometry is always important. You know, in life, you never know what comes your way. That's when anytime you are privileged to learn anything, excuse me, anytime you are privileged to learn anything, learn it. Because you never know when you will need to know to use that concept. So we have used the concept of stoichiometry in this case now. What does it mean by come again? Your question, Winnie. Yes, the reaction. Why did you multiply? So our question says how much it is given off by 4.5 kilogram. The energy that we know, this is what we have. We know that 1 mole gives off 890 kilojoules of it. And we are given 4.5 grams. So how do we relate that? It's either we convert this one to gram or we convert this to mole. Well, logically, it makes sense to convert this to mole. So we convert it to mole. So how do you convert 4.5 grams to mole? Number of moles is What is a lot? Number of moles is mass over molar mass. We know the identity of what we are working with, so we can always get the molar mass, which is 16 gram per mole in atomic unit. So let's get the number of moles. The number of moles will be 4.5 over 16, 0.0821. It's given off will then be, so for 1 mole, it's given off is minus 890. So what will it be for 0.281 moles? I already said it. When you're dealing with thermodynamics, it is important. How did I get molar mass? I am not going to answer that one. It is important to always write the state of the matter. Always important to write the state of the matter. Is the negative sign important? Yes. What is the ending that you don't get? That's what I wrote here. So 1 mole is equivalent to minus 890. So what about 0.281 moles? Secondary school, if you're asking all these questions. So this is a review of your secondary school now. Let me work this last example. So when 2 moles of H2 gas and 1 mole of oxygen react, so 2 moles of H2 plus 1 mole of oxygen react to give water. So that will be 2. This is the amount of it that is given up. So if that amount of it is given up, it means that our delta H is equal to minus 572. I thought it was methane that we were dealing with. I did not. Where did I write the molar mass of oxygen? Please, at praise, calculate the molar mass of methane for me. So what is the amount of it involved for this reaction? So can work also be in equilibrium like it? So that would be mechanical equilibrium. So when you have mechanical equilibrium, the work done is balanced. So 2H2 plus O2 gas going to 2H2O liquid, delta H is equal to minus 572. So this is, sorry, before. So we have to calculate the heat change for this one. So the best way, always look, thank you goodness, the molar mass of, why did I multiply 0.81 mole by instead of 890? What is delta H for the reaction? Lookman, tell me. Then we'll continue the question. So H2, what is delta H here? So what do we look at? We look at this expression and compare it to this expression. What I see between these two expressions is that, so let's call this equation 2 and this one equation 1. So if you look at equation 1 very well, you would realize that equation 1 has been divided by 2. So equation 2, so this is our equation 2. Equation 2 is equation 1 divided by 2. Because our enthalpy is what did I call it the other? Extensive property. It depends on the amount of substance. Once you divide this one by 2, you also divide that by 2. So because this is for the reaction multiplied by half, if you're multiplying something by half, you're also dividing by 2. So you have delta H to be minus 286. Oh, okay, that's what somebody wrote the other time. So the second one, 2H2 gas, sorry, so this should be 2H2 liquid, not gas. 2H2 gas. So comparing this one, so we call this equation 3. So equation 3 is reverse of equation 1. So what do I mean? You have flipped it over. You have put the reactant in the product side and the product in the reactant side. So the delta H will be 572. Okay. In those days, when we are clapping for the teacher, it's usually means that the lecturer, it's time to go. So I'm looking at you doing thumbs up, meaning that I've overstayed my teaching. Anyway, so whether you stay in before or not, don't say. This was where I intended to stop. And I intend to finish this one on Monday. So I hope we start early on Monday. Any other question, please? Because I'm about to end the session for everybody. That is not a question. I do understand it is not a question. Edun Adeoluwa Joshua, type your question. Okay. Will we have to convert units at any point in time? If it is necessary. Does that mean the third reaction? Yes, so the third reaction becomes endothermic. Is the reverse equation positive or negative? I wrote it there now. Look at it. Should be what they told us in mathematics. If you don't have any sign in it, it means it's positive. Please explain the last part of the question again. Which last part? Why did I multiply the first one by half? Can you listen to that? Sorry. I multiplied it by half because when I compared it with the original equation, let me see if it will allow me to expand it. Come on. But you must cancel kilojoules. I did not cancel kilojoules, I beg. So this is the original equation. If you compare it with this one, you will see that this equation 1 is 2 of equation 2. Oh, please take a look at the slide again, then you would understand. If you have another class, you can go. Let me. I can. I can attend to. Yes, the third reaction is now exothermic. Why did the negative sign change to positive? Whoever Zoom user is. So the negative sign because we reversed the equation. Reverse in the sense that the reactants are now on the product side. So that's what it means to reverse a chemical equation. So you put products on reactant side, reactants on product side. Once you do that, the sign of your delta H changes, meaning that even if your delta H was originally positive, it will not become negative. Please, ma, how did you get the delta H for equation? Okay, so that's the same thing that I just explained. So when I compare this is equation 3. I said it's liquid, please. When I compare it with the original one, I saw that it's the reverse of or reciprocal of that. Any other question that I have missed? Okay, me say I have tried, Been talking for 1 hour. It's not easy to talk. Zoom user, that's good. You are now answering other people's question now. Why is there no minus? So at Aziz, I have just answered that one. So I hope that you got it in time. All right. So thank you. Please let's be earlier on. So which one at Shoaib Khadija Kende? Which one? What are you exactly referring to? Liquid to gas, doesn't it mean that it's so? Where is the liquid to gas? Liquid to gas. We're not directly converting to water. No, okay. To be sincere, I'm not sure I get the question. Liquid to gas, doesn't it mean that it is involved when the equation 3 change? All right. See you all on Monday.